The aim of this norm is to translate this block diagram into a standard diagram for all those technicians and engineers who are concerned about the design, the setup, and the use of control structures. As you can see here, the name S5.X means that there is a group of norms which are gathered under the same umbrella, that is S5.something. As you can see here, this group of norms talk about instrumentation symbols, binary logic devices, then distributed control logic and computer systems, instrument loop diagrams, and process displays. So first of all, we're gonna have a look at this block diagram, and we're gonna check the equivalence of these two diagrams. So how can we translate this block diagram into this new standard diagram under the norm? As you can see here, we have the set point. The set point is the desired value for this process variable. This process variable is the variable which we are interested in to measure and to make this process variable to behave in some specific way. So we want the performance of this variable to be equal to our set point. So we compare our desire, our reference, this set point, with this process variable by means of the PID controller, which is the standard one, and this PID controller calculates electronically the error signal. The error signal is the difference between the set point and the PV variables. But be careful, the PV enters the PID controller when it's translated into an electrical variable. As you may know, here we can have a speed, for example, a linear speed in meters per second. We can have an angular speed with RPMs, for example. We can have a temperature in degrees, and so on. So here we have physical variables. These physical variables in general are translated into electrical variables in volts or milliamperes by means of this sensor device, or by means of the sensor. So two electrical variables are compared within the PID controller, and the PID controller applies some control law we're gonna have a look later on, and this controller calculates which is the optimum output for the process. When I say the optimum output of the process, I mean that this manipulated variable, this controller output, will make this process variable to behave like the set point, like our reference signal. All of this under external disturbances. As you can see here, these disturbances may affect the behavior of our process, the performance of the loop. So this is the classical feedback loop. We say that this is a feedback loop because, as you can see here, the output of the process, the output of the system, goes again into the process as an input. So that's the reason why we say that this is a feedback control loop. Well, as you can see here in the diagram, we have a pump in here. The pump is producing an inflow to the tank, as you can see here, this tank, and we are measuring, as you can see here, we are measuring the level of water within the tank. As you can see here, there is an L. This L is for level. This T is because this is a sensor or a transmitter. So sensor and transmitter is at the end the same word. They are synonyms. So this is the sensor. So because this element, the LT1, is the sensor, the number will be explained later on in the next slide. But this element is a sensor who measures a general PV, as you can see here, this PV, into an electrical PV, this PV, okay? This PV is electrical, this PV is a physical in general, this is the level, which is translated into an electrical value, which is compared with the set point within the controller, the level controller, as you can see here. The difference between these two elements, this is a transmitter, this is a sensor, while on the other hand here we have a controller, but both are for the level of the tank. That's why they have in common the same first letter, who is L. As you can see here, this is the output of the controller, which is MV, the manipulated variable, the controller output, the controller action. And this action is applied to the pump, which speed will increase or decrease depending on what's the decision of the controller, which depends at its time on the difference between the set point and the PV, so the set point and the real process variable. What about the meaning of the letters? As you may remember from the preceding slide, L is for level, so T will be for temperature. For example, E will be for voltage, F will be for flow, and so on. So a transmitter that measures the temperature in a room, in a tank, whatever, that measures the temperature, will be defined as a TET, which is a temperature transmitter, and a controller that applies the controller action on the error about a measurement of a temperature, of the temperature of a tank or in a room, will be a TC, which is a temperature controller. So here we have TIC, sorry. This is T for temperature, this is C for controller, and this letter in the middle, E, is for indicator. Indicator. That means that the device, the transmitter itself, has a display that indicates the temperature that is measured. That's the I in the middle. But you can have not an I, but an R. This R is for register, for record. So that means that the temperature, for example, TRC, means that it's a temperature controller, but it records the data on a device, for example a data logger or something similar. Okay, so this recording property means that we can have access to this data later on in a memory device. What about this number? This 103 means that we have several elements, for example controllers, transmitters, and so on, and all of them are related to the same control structure. We can have in a diagram different temperature controllers, but these temperatures may not have nothing in common. So then we may have, for example, TYC 102, for example, TYC 103. These are both temperature controllers, but their temperatures, they have nothing in common. They belong to different control strategies, control loops. Well, here you have a table that gathers all together the meaning of the letters depending on the position they are. As you can see here, this is the first letter. As you may remember, we have succeeding letters. So, as you can see, the T as a beginning letter is for temperature, but the T as a succeeding letter is for transmitter, for transmit. And as you can see here, the C as the last letter is for control. And what about this letter that's in the middle? It can be for indicate, DI, but it can be for record, VR. As you can see here, the device can have some numbers around it. These numbers are for the pins or for the connections, for the electrical, for the physical connections of the device. As you may know, the device has a rear panel, and this rear panel has several pins, and these pins are numbered from 1 to N. So these numbers here, the meaning of these numbers is these elements, these pins in the rear panel. So, for example, this can be connected to the supply, to the electrical supply, for example, 24 volts direct current. So this helps us to understand how this device is connected, for example, to the devices which are around it, or for example to the supply. Well, all the signals and supplies, they have a specific way of representation in this norm. As you can see here we have a pneumatic signal. For example, here this pneumatic signal is represented like this, but an electric signal can be this or this, while an hydraulic signal is symbolized like this. A capillary tube like this. An electromagnetic signal, when it's guided, is represented like this. When it's not guided, for example, a radio signal or similar, is represented like this. As you can see here, the links, when they are software or a computer link, is represented like this, but when it's a mechanical link, it's represented in a different way. What about the supplies? Here we have the air supply, the electric supply, the gas supply, and so on. But pay attention. Typically, the supplies are specified. For example, an electric supply of 24 volts direct current. Let's talk about the actuators, specifically about the valves. As you can see here, we have the symbol for a diaphragm valve. This kind of device, this actuator, needs a pneumatic signal. Okay, we're gonna see later on in our diagrams. This is an electric motor. This is actuated by means of a solenoid, and pay attention that this is a manual valve. We're gonna see later on in a diagram. Let's have a look at this example. As you can see, we have a lower tank in here that is filled with water. Here we have an upper tank, and a pump makes the water from the lower tank to go as an inflow to the upper tank. Here we have two valves, and these two valves are manual valves. Okay? Then, as you can see here, we have the set point, which is an external set point. We have the process variable. This is the process variable, but this is translated into an electrical. So here we have centimeters, for example, but here we can have volts or milliamperes, depending on the technology of the sensor, of the transmitter. As you can see, L for level, T for transmitter. Here, L for level, C for the controller. So this will be the manipulated variable. This manipulated variable, which is electrical, applies a voltage to the motor. The motor helps, well, makes the pump to make the water go to the upper tank. Let's have a look at these several feedback control structures. As you can see here, we have a level control structure with a different number of this level control structure to make the difference between them. As you can see here, we have the set point. This is our level, the level we desire in this tank, but this is an electrical value. Okay, this is the process variable. This is the measured process variable, while this is the controller action, again to a pump that makes water to come as an inflow to this tank. As you can see here on the right side of the slide, we have another control loop with a set point, the process variable that is measured, the real process variable, the controller action or manipulated variable to this pump that is emptying the tank, not filling the tank. Here we have a different control structure with a set point for the flow here in this pump. Here we have the process variable. Now it's not level, it's flow. This is the flow translated into an electrical value, which is compared to the set point, which is also an electrical value, and then the manipulated variable, as a result of the controller action, is applied to the pump. Let's have a look at this final example. Here we have some product that it's incoming by means of the opening or closing of this manual valve, as you can see here, into a heat exchanger. This product is heated out because steam is coming also into this heat exchanger. So the steam that is incoming to the heat exchanger makes this product to be heated. As you can see here, we measure the temperature here in the heat exchanger. Then this temperature, that is the process variable, is translated into an electrical process variable, and this variable comes to the controller. The output of this controller is sent to a device that changes, that translates an electrical variable. This is electrical variable, this is the manipulated variable. This device changes this electrical variable into a pressure. That's why current into a pressure. That's the role of this element. So this element, this letter Y, that is a letter that can be defined by the user, but it's commonly used as a translation device. This device translates an electrical variable into a pressure variable. Why? Because this diaphragm valve needs a pressure as an input. As you can see here, this controller is very important. Have you noticed that there is no incoming arrow? Because the set point is not external. This controller is a TIC. That means that we have a device with some kind of an interface that indicates the value, for example, of the PB, of the NV, and also it has a keyboard. This is a keyboard or some cursors in here that helps the user, that allows the user to state the set point value. So that's why this diagram has a controller which has no external set point, because most of the controllers they are equipped with a keyboard that allows us to state the value for the set point. So the set point is defined internally by means of this keyboard or by these arrows. Let's have a look to this additional example. As you can see here, we have again a flow control loop, as you can see here at the top of the figure. Again, this is the process variable. This is the flow that it's measured and translated into a process variable, but now this is electrical. The manipulated variable is in here. As you can see here, this diagram is simplified because again we have this kind of valve and this element is missing. So that's why I say that this diagram is simplified. Then here we have another flow control structure. As you can see here, there is no external set point, so the set point is internal, and again here there is no set point which is external to the device. As you can see here, again we have a level controller here. Again, the set point is internal, so the user is stating the set point by means of a keyboard or something similar. Here we have the PV, and here we have the PB which is measured. Here we have a new diagram, a new control loop. It's also a feedback control loop, but this P is for pressure. So that's why here we have P for pressure, T for transmitter, so this is the process variable, this is the process variable electrically translated. Here we have the PC, which is the controller. Again, the set point is internal, and this is applied into a valve. As you can see here, again, the diagram is also simplified because here an I to P block is missing. This, the name of this block would be PY according to the norm.